Well, welcome back, everyone. Looks like we can get started. We've got two representatives on the in-person section and two representatives from the land of Zoom. So welcome back, everyone. We're now on week 9. So this is the point at which the semester feels like, at least from my point of view, feels like it starts to get going really quite fast. Week number 10 is going to be right before spring break. And then we're nearly done with the entire semester. There's only 4 more instructional weeks after we get through that one. And then week 16 is just for the final exam. But the major announcement of the day is definitely that we are coming up to our second exam. It'll be a week away from today. And for everyone who's in the in-person section, I sent in this inbox system right here in Canvas instructions on how to schedule your exam in the Idaho Falls Testing Center, Pocatello Testing Center, and otherwise. For people in the in-person section, we'll have our exam in the classroom on this date. Well, any questions at the moment, folks, about the exam scheduling or the exam itself? Okay, well, let's just reiterate a couple comments we made about exam one and exam scheduling because it has been a while. Because the testing centers, Pocatello Testing Center in particular, can get pretty overloaded around this time of semester. Because exams are being sent to the testing centers, they do have to work with your schedule. So you don't have to take the exam at 1 o'clock, but if you find that time slot useful, that's a good time for it. We won't have a class on next Monday so that people can schedule their exams at any time, in particular 1 o'clock. But also the exam is going to be completely open to be scheduled between the 16th, Monday, and the 19th on Thursday. So whichever day just works best for you, you're welcome to schedule. And that does cause a fairness issue with the in-person section. I'm not sure if I mentioned these comments before, but even if I did, let me reiterate. For the in-person section, just because the online section can schedule on an entire range, same applies for the in-person section. I'll just be here on Monday, 1 o'clock for the exam. If that day works great for you, that's when we'll take it. But if you need to take it on a different day, just like the online section, it will be open on these 4 days. Just let me know and I can have your exam, even in the in-person section, sent to say the Idaho Falls Testing Center. So that's again just the major spiel I usually say right before our second exam. If you've already scheduled your exam, thanks for doing so. And if you haven't, please get it done as soon as possible. That way you can make sure that your time slot that's most ideal to you doesn't get filled up. As far as the coverage, it's going to be chapters 14, 15, and 17. Even though we're probably finishing chapter 18 today or early on Wednesday, I didn't want to go too far into the content. I feel like this is a good amount of concepts already. So chapter 14, it's either going to be a confidence interval or a hypothesis test, where a population value for sigma, population standard deviation, is known. Chapter 15 has 2 different problems I'll ask. One is going to be finding the right sample size to target a margin of error for a confidence interval. And the second one will be about type 1 error, type 2 error, probability of a type 1 error, and power. Again, there'll be just an emphasis on concept questions here. And then chapter 17, again, it's either a confidence interval or a hypothesis test. So one problem from chapter 14, one from chapter 17. And if I pick a hypothesis test in chapter 14, the chapter 17 problem will be a confidence interval and vice versa. Well, best way to prepare for the exam, again, just reiterating comments, get fully caught up on these chapters and you'll be in a great shape for being prepared on the exam. After you're caught up, take a look into these 3 different files down below. This is going to be the last page of the real exam 2. So this will tell you what information is provided, what you have to have memorized. And the same kind of versions of sample exams 1 and 2, these are meant to show you what a concept question would look like in an exam setting, where you'll still need a calculator. A good scientific calculator is required, but these questions are written so R is necessary to get through them. So any critical number like T star or any p-value is provided on those exams. And you're just saying, what is the parameter? What are the conclusions? You'll calculate some standard errors, some test statistics, degrees of freedom, and those kinds of things, but nothing that goes beyond a basic scientific calculator. And that's pretty much it, my spiel for starting this out today. Any questions at all, folks, about Anything we've talked about so far? Okay, well, after that second exam, we'll have one more exam to get through, but we'll be doing everything in just another complete kind of setup just like this in a very parallel way. Exam 3 is probably going to be something like chapters 18, 19, 20, but we'll see where we end up when we get to that point after the spring break. For the moment, we're in chapter 18, and here's where we left off. Really on example 3, actually. This is not quite where we left off, but I think this is a good warm-up coming back to the example 3 problem across a long weekend. So the major thing that we did at the top of these notes was we were discovering what the sampling distribution should be for x bar 1 minus x bar 2. And there's a lot of context that goes with this already. We're saying that we have two independent simple random samples that we've measured. Then we're taking the difference in the statistics, the difference in the sample means. We found that this should be distributed normally by looking through a probability theorem. It's a normal distribution with the center at mu1 minus mu2. So both statistics x bar 1, x bar 2 are estimating the population means. And so if we subtract them, it seems logical that the center of this normal distribution should just be the difference of those parameters. Then it got a little bit more complicated for the standard deviation. It worked out to square root of sigma 1 squared divided by sample size 1 plus sigma 2 squared divided by sample size 2. From there, we made an estimate that sigma 1 is approximately equal to the sample standard deviation S1. Likewise, sigma 2 is approximately equal to S2. And by making this jump from here to here, it gave us the standard error for the problem. So that's our brand new formula. And once we have that piece, we just loop it in right here. Now we have a confidence interval. We divide by it right here, and we have the new test statistic. And really the only thing that became computationally kind of intense is whether it's a confidence interval or a hypothesis test to get the critical number T star or the p-value. Our methods are based off these degrees of freedom here. We calculated them once in the notes, and this will be something we'll have to be ready to go with on exam 3. That formula will be probably provided, though, to help us out. So that's the rundown of the method so far. Any questions or comments at the moment? Okay, now down below, just a roundup of the p-values using pretty much the same exact syntax as we saw in chapter 17. And here's the problem that we were analyzing. It was a pharmacology study published in the Toxicology Journal. They gave 6 rats in the treatment group an exposure to a certain level of toluene, I never know how to pronounce that right, and then they measured the amount of dopamine in the striatum region of the brain. Then, because this was a bona fide experimental design, they needed a control group, so they had 6 rats that were just living their lives, not exposed to anything, in the control group. And this is the mean measurement of dopamine. This is the standard deviations of those measurements. And we just rephrase them in these terms right here. We set exactly what our parameters will represent. Mu1 and mu2 will be the mean dopamine concentration. We abbreviate it there, not saying striatum region of the brain. Mean dopamine concentration for rats in the toluene group and in the control group respectively. Then we work through the standard error formula, the one that we saw at the top of the notes, just plugging in the sample data to get this value, 285.4972. And then this is just a copy of the standard error formula. We took this value 285, plugged it in, as well as those statistics you see above for toluene group and control group. We found the degrees of freedom is 9.14. But critically, just as a reminder, the brilliant idea behind these degrees of freedom is we never once made an assumption that the sample standard deviations are equal. Well, let me say that better. That the population standard deviations, sigma 1 and sigma 2, are equal. And in fact, looking at the sample standard deviations, they're kind of unbalanced. That's evidence that they weren't equal in the very first place. So this does not make any further assumptions on the population standard deviations. And it gives us a more honest degree of freedom, which is going to capture a wider interval for sure. But when we say 95% confidence, that's going to be a much, much more accurate statement rather than if we used, say, 10 degrees of freedom, the pooled sample procedure. Well, with all that put together so far, next thing we need is the critical number T star. So here's what we would have done in syntax if we're writing this out to say in RStudio. T star is going to be use the quantile function. So start with Q, put in T because this is a T distribution problem. Then next, what we put inside is, if it's 95% confidence, we just use this structure. 1 minus 0.95, divide by 2. The next input is the degrees of freedom, and 4 decimal place of rounding is pretty appropriate for this context. 9.1420. And then just to force it positive, put in lower dot tail equals false. Although I don't think anyone could complain if you gave me a negative T star. It's, again, part of the confidence interval, both the positive and the negative values. So that's the entire syntax, pretty much the same syntax we used in chapter 17. The only difference is degrees of freedom never had to be an actual round whole number. It can be a decimal number like this one. So let's just throw this into the calculator. Quantile for T distribution, 1 minus 0.95 halves, 9.1420, lower dot tail, set false, gives us this value altogether. So 2.2568. And once again, some really very broad generic advice for rounding. That's very, very general. 4 decimal place works pretty well for degrees of freedom. 4 decimal places is appropriate for, say, a critical number. And if we were doing a p-value, we'd go for 4 decimal places as well to approximate. At this stage, we just put everything together and compute the confidence interval. Any questions on getting the critical number first? Okay, so we need to look inside a couple things when we're building that confidence interval. We need the standard mean, or excuse me, standard error for sure. We also need the 2 sample means. So let me just take kind of a blunt screenshot. That way we won't be scrolling up and down a whole bunch. So there's our information below. We also have our critical number right there. So everything is all set up for the confidence interval. I feel like this should be on the next page though, just so we're not trying to squeeze it in. So first, let's just put down the method. We're taking x bar 1 minus x bar 2 because we're estimating the difference in means. Then we subtract a critical number T star and multiply it against a new standard error, which we call standard error of x bar 1 minus x bar 2. Next, make the substitutions carefully. So for x bar 1, it's going to be 257.8.0. Then for the sample mean, 1880.4. Then subtract from that standard error, 285.4972. And multiply it against finding the critical number we just picked up, 2.2568. So there's our entire confidence interval. All we have next left to do is compute it, then interpret it. Always, this is kind of the fun stage because the parts we were working through are just trying to get us to a decent logical step-by-step process. So we can just substitute everything at once we get into part E. And this again is a problem you're going to see in, say, an exam 3 setting. This is written as a typical exam problem where you'd work through the calculator, but the critical number T star, much like on exam 2, that part's provided. So now it's a calculator operation. Let's get this in accurately. starting on the lower bound part, I'm going to type in all these numbers. And I did forget one thing. That's kind of a weird omission. I put a minus in the middle of those two. Don't forget it's a plus and a minus. So let me fix that. And then I'll do the minus part first. Should have went plus and minus. Let me highlight that in yellow. I'm going to blame daylight savings on that mistake. Then plus and minus on that one. Okay, now we're in better shape. So go 2578.0 minus 1880.4. Those parentheses aren't required, but I find I make a mistake, a weird one, if I don't put it there to really group those together in my mind. Then 285.4972 times 2.2568. Then double check these numbers. Okay, and this is a good comment to make on our exam 2. If you're doing something like this on exam 2, definitely put this down on paper, because if you make any mistake down here in your actual calculator, I'll be giving almost all of the partial credit on what it looks like here. This is the major concept. I'm not trying to assign a lot of points on the concept of just typing it into the calculator itself. So for our lower bound, I'll round this now to just say 3 significant digits at this point. 53.3. I believe the units were nanograms of dopamine per, I think it was gram of the Stradian region of the brain tissue. Let's double check those units. Kind of a morbid study when you think about it. Yeah, nanograms per gram. I'll use the same GM for gram abbreviation. This is going to be less than mu1. Let me go back to that color coding where blue is for the treatment group and green is for the control group. So mu1 minus mu2 less than. And if you're confident you got in your calculator once, use the feature to put the last computation back on screen and change that sign to positive right there. The mistake I sometimes make is I accidentally change that one where the red dot is to positive, but that has to always be minus. So it's just that sign in the middle that flips to positive. And this will be 1341.9 nanograms per gram. Okay, that's 4 significant digits instead of the 3 over here. I'll just say I'm rounding to the nearest 10th instead on the rounding. So we did it, folks. That's our entire confidence interval. All that's left now is to interpret it. And it looks like a follow-up question down below will address at the same time. Now that we have this interval, sometimes when there's 2 means or more, or 2 population proportions or more that we're analyzing, the interpretation you give can get kind of unwieldy. So there's kind of a nice trick to this to make the interpretation kind of flow a little bit better. This study is really all about the treatment group. Rats that were exposed to the chemical toluene. So if that's the treatment, it's the one we really want to emphasize when we give a practical interpretation. So it's a good additional step, although not required. For the sake of making the interpretation flow better, I'm going to rearrange these 3-sided inequality and solve for mu1. So another way to package this is call this mu2 plus 53.3 nanograms per gram is less than mu1, which is less than mu2 plus 134.1.9 nanograms per gram. So now when we see it this way, the treatment's been isolated, and we're essentially going to say the treatment group is from 53.3 higher to as much as 1341.9 higher than the control group. And that's just an easier sentence to put down on paper. And if you were, again, trying to tell people what your study is all about, that flows so much better that people aren't just going to nod and grin and pretend like they understand you. There's a good chance they're going to know exactly what you meant. So now we're up to the practical interpretation. Any questions or thoughts getting to this point in part E? Okay, again, even though this is an exam 3 problem, if you were doing, say, a confidence interval interpretation on exam 2, here's how it would go. I'll ask you to state a parameter, so it'll be stated once. So reference this. Here we have two parameters is the only difference. Come down below. I realize we can't copy paste on a real exam. That's just where your eyes are looking. We'll imagine it that way. And whatever you have here for either the confidence interval or whatever it is for a hypothesis test, just read it out again, saying what you said the parameters were in the very first place. It means you have to read out the parameters twice on an exam, and I know that's tedious, but we're keeping the exam short so you can take the time to write them down twice. And I found that if I don't ask the part A, it's usually a lot less likely we're going to get part F down correctly. So it has its purpose. I know it's tedious, but we'll be reading them out twice in class as well, and for the sense of solidarity. So even though, again, this is a two-sample interpretation, it flows very similarly to the one-sample interpretation, just one parameter versus two. Start by mentioning the confidence. We have to have that down on paper somewhere. So we'll say, with 95% confidence, we can't say there's a 95% chance. We can't say with probability 0.95, any of those things. What we have to directly say is confidence. It is still a probability, but the probability isn't about mu1 being in this spot. The probability is from the whole method, from the start of the design to selecting the sample, computing the statistics, and then finally getting to that point on the red dot, actually having mu1 and mu2 exactly where they are. Instead of saying all that, we just say, we're 95% confident that our procedure was successful, and either mu1 minus mu2 is in these bounds, or mu1 is in those bounds relative to mu2. So again, for short, just say 95% confidence, but avoid probability or say percent chance. Then next, we're going to start by reading from the middle, then left and right, involving mu1 and mu2 and the way we said them. We'll say, what was mu1? The mean dopamine concentration for rats exposed to dopamine. So let's say that right now, focusing on this spot. The mean dopamine concentration for rats exposed to toluene. Okay, so we're done with that part. Now I want to focus on the numeric part, the 53.3, 134.1. We also have to focus on the sign. If I have a positive here, I'll say larger at this point. If this was a negative, I would have said is less than this amount and up to this positive amount. So make sure the signs you see is also reflected in the language you write out. So I'll say is from 53.3 nanograms per gram larger, and say smaller again if that was a negative sign, to 1341.9 nanograms per gram larger than. So now we have to say larger than what? Now we're involving mu2. So we see what we said it was, mean dopamine concentration for rats in the control group. We already said dopamine concentration once, so we just have to mention then the mean for rats in the control group. And that does it. Again, it's kind of unwieldy because there's two parameters at the same exact time we have to mention. So we had to be very careful to use the description we used. Once again, here in reading out this interval. And if you decide to keep it where the red dot is right here, the verbiage would have been a little bit different. You would have said the mean dopamine concentration for rats exposed to toluene, or let's start over. Again, it's kind of unwieldy. You might have said the difference in the mean dopamine concentration among rats exposed to toluene minus, you have to keep the direction there, rats in the control group, is from 53.3 to 134.9 nanograms per gram. It's a fine way to say it, but again, it's easy to get kind of confused. We're saying really directly that the toluene group is this much higher to as much as that much higher than the control group. So I feel like solving this and writing it in this form is the better interpretation. I'll give full credit for both. Well, we did it, folks. That's the rundown on that one. Any questions at all getting through that interpretation? Okay, again, this was a larger study, really. It was published in the Toxicology Journal. This was back in, I think, this late 70s or 80s. It was all about people abusing inhalants, and they were looking for just what exactly were these inhalants doing. They found it absolutely increases dopamine, and potentially by a lot. But notice the lower bound is just barely above the control group. This was just done in rats. They can't do the same experimental design in humans. That had been totally unethical. But now the last question, part G, says, does the study provide significant statistical evidence that exposure to toluene causes an increase in dopamine levels in rats? And one word inside here is more important than the others. It's a word about cause and effect. Because this was an experimental design, we can use cause and effect language. They did everything right in the study. They randomly assigned rats to the toluene group and other rats to the control group, more likely than not, because it was published in the Toxicology Journal. Another reason why we can say yes to this is also the interval only has positive values. If this was, say, a negative right here, we'll flip this back in a moment. But if it was negative in these spots, then it's absolutely conceivable that mu1 minus mu2 is 0. That mu1 could be less than that amount, or as much as this much higher than that amount than in the control group. So if we had a negative, we would have had no statistical significance whatsoever. So statistical significance, this portion, is just the fact that it's actually a positive in these values, not a minus sign. Then we can say cause and effect language because it was an experimental design. So putting that all together, does the study provide significant statistical evidence that exposure to toluene causes an increase in...
When we have onions?
Sorry, say again?
Patty said they were in the garage the other day.
Oh, sounds like an open mic. So putting that together, we can say yes, because the interval only has positive values. So that part gives us the statistical significance in the problem. As far as cause and effect goes, we can say, and cause and effect conclusion is appropriate because this was an experimental design. Then finally, that's the conclusion. We got through our first two sample mean problem. And we did it as a total confidence interval. So what we would like to do next is show how to do it as a hypothesis test. And at the same time, show how to do it where you're making RStudio work with the actual raw data if you have it, just like in the next example. But before we do that, another thing we didn't do in this problem is, notice we didn't have a very big discussion whatsoever on condition checking. Condition checking gets a little bit more involved than we saw in chapter 17 in the current chapter. So that's what we're going to focus on next before we turn to the next problem. So here are the conditions for the two sample mean procedures. There's statements on robustness that we're going to take a careful look at. And then the conditions for the two sample t procedures, this part right here is asking that we have a simple random samples from two distinct populations, and the samples have to be independent. So one sample cannot influence the other one. The next requirement, condition 2, is both population means are unknown. But again, that's the default assumption. And likewise, sigma 1, sigma 2 are unknown. But a little bit more to say on that. Sigma 1 and sigma 2 are so unknown, we don't even assume that they're equal at any point in our procedures. As far as this goes, if you skipped this in condition checking, that would be okay, because that's the context of this problem. We're doing this entire statistical procedure because we know mu1 and mu2 are unequal, and there's no assumption whatsoever. Sorry, let me just fix my formatting with Control Z. There's no assumption whatsoever in sigma 1, sigma 2 being known. So here, this is safe to skip, if you choose to do so. No harm done if you did want to discuss that part. Here, we'll briefly discuss. We'll see if we have information on the samples being random. We'll see if there's anything that can convince us that the samples are not independent, if somehow maybe we're doing a before and after study on the same person more than once, the data would be dependent in that case. So if the sample data is independent and we have a random sample, next thing we do is we check the combined sample sizes. We have that this procedure is effective, and this is just a restatement from above on the notes, if the sample sizes are both, for both groups, at least 5. So if we try to run this procedure where one sample had 3 or the other sample had 4 observations, it would be inappropriate for this method. We should switch to a non-parametric test, or just try to get a larger sample size. But after we look into that, this is almost a copy of what you saw in chapter 17. The number values are almost the same, 16 instead of 15. Again, here, this number is about the same. And the language about outliers and skewness is identical as well. The major difference is we're looking into the combined sample sizes. So when we discuss robustness on this, if we have one sample with 20 observations, another sample with, say, 30 observations, our combined sample size is going to be 50 altogether, and that would put us in this bullet point. The procedures will be safe unless there's clearly skewed distribution, or excuse me, this will be safe even for clearly skewed distributions, unless we had just loads of really egregious influential outliers, then the total sample size needs to climb probably into the hundreds to overcome it. But again, where the red bullet is right up here, this is the new part. Robustness becomes a pretty interesting discussion when we're looking into 2 independent samples. So let's carefully look at what the author is saying for this portion right here. The 2 sample T procedures are more robust than the 1 sample procedures than we looked at into chapter 7, even particularly when they're not symmetric. So if we have skewed data, we're pretty concerned in chapter 17, but not as concerned in chapter 18, analyzing the difference between means. It says next, when the size of the 2 samples are equal and the populations compared have distributions with similar shapes, the probabilities are accurate when the sample sizes are even as small as n1 equals n2, which is 5. If the sample size, or excuse me, if the populations have different shapes, we'll see it in the sample data, and that is bad. We're going to need larger sample sizes. And we have even more robustness when the sample sizes are equal. So here's 2 kind of situations that can occur. You might have 2 simple random samples that gave you data that looks like this. If you have data that's skewed to the right, maybe even an outlier in there, so that's sample 1. Here's sample 2. This one's also skewed to the right, maybe even a little bit worse, and a slightly worse outlier. Sample 2. So this would be actually not bad of a situation, as long as our sample sizes are large enough. If we say have sample sizes maybe even in the 20s, we're going to be okay because of the higher robustness that we have, particularly when they're similar shapes. for the two sample methods. So we can say here, our procedures are more robust in this situation, where we now have similar shapes, both skewed to the right. But if the shapes are different, if one is symmetric and the other skewed to the right, or even worse, if they're skewed in opposite directions, then we have a problem and we're going to need pretty large sample sizes to overcome. So if we have something that goes like this for sample one, let's make it look about the same, skew to the right, substantially, and maybe a mild outlier, but sample two goes like this. This one's skewed to the left. And let's say not even an outlier, the fact that they have now non-similar shapes means in this case, the T procedures are less robust and a pretty large sample size is going to be needed in this situation. Possibly the combined sample size should probably be around 60, 80, 100 for this kind of situation. So less robust, a larger combined sample size is required in this situation. So that's what the robustness new discussion is all about. We're pretty happy if we see this, and we're even more happy if both distributions are, say, roughly symmetric, no apparent outliers, then we're in great shape. But real world data does get messy, and it's just a bonus that if we're looking into the difference between two means, this is not as big of a cause for concern, less of a red alarm like this kind of situation is on the right. But that means we have to do a lot of extra analysis when we go to check conditions, like we're going to do in the next problem, to look into how well our sample procedures are going to pass the conditions. We must produce histograms for both samples and discuss robustness. One common mistake when we discuss the robustness is how robust the test is, how accurate our p-value might be, or how accurate our confidence intervals margin of error is going to be, depends on the sample size as well. And we're looking into the combined sample size. So we have to mention that in our discussion as well. Be sure to discuss how the combined sample size N1 plus N2 influences robustness. So lots to talk about on condition checking out of nowhere, but we're going to practice that on our very next problem. Any questions or comments so far, folks, about anything we've said so far? Okay, I just want to keep the parallelism that we were starting off. We just go by what the problem tells us on randomization here. This is the default setting for statistical inference, so you're safe to skip part 2 on the conditions. But condition part 3, this is where we're going to analyze completely to make sure our data really fits into the picture and the two sample methods are appropriate. So here's the problem we're going to practice out. So we have a column that just says normal, another column that says schizophrenic. This is 20 observations here, 20 observations here, quantitative data. And it's a pretty controversial data set for a lot of different reasons, but it makes it an interesting one to analyze. This is real. It was published in the Journal of Abnormal Psychology in the 70s. And it's, been over a half a century later. A lot has changed in psychology since then. So we're looking into some pretty interesting data at this point. This is about the thematic apperception test. I'll just call it TAT for short. The thematic apperception test presents subjects with ambiguous pictures and asks them to tell a story about them. So this is kind of a weird test. You could possibly imagine this in popular culture, this happening whenever a character visits a psychologist or a psychiatrist of some kind. We're told next, to getting closer to the actual context of the study, the stories can be scored in several ways. Just depends on what they're trying to measure. And so these three authors, Werner, and I can't pronounce that person, and Paulhan, asked mothers of 20 normal and 20 schizophrenic children to complete the TAT, I'll say for short. And here's how they scored them, and scored the number of stories out of 10 that exhibited a positive parent-child relationship. Already that sounds pretty controversial in my opinion, because they're going to have to define with a lot of words what they meant by that, what it means to exhibit a positive parent-child relationship. Also, notice that these are two different populations. They had 20 mothers of normal children, however that was defined in the 70s, and 20 mothers of schizophrenic children. These were being asked of the mothers to complete the TAT and scored the number of stories out of 10 that exhibited a positive parent-child relationship. Now, this data is pretty dense when you think about it. And when I read a problem like this, probably my first assumption that I have on the first read through the context was these are ordinary children, these are schizophrenic children, and they were showing pictures to the children and looking out the number of positive parent-childhood relationships, number of stories that exhibited positive parent-child relationships, stories given by the children. Well, let's read that again. I don't think that's actually what's going on here. So it says, asked mothers of 20 normal, 20 schizophrenic children. The mothers were completed the TAT test, the thematic apperception test. So all we know is that the mothers had normal children or a schizophrenic child or children. Then the mothers were shown random pictures. Then they had to tell a story about it. And then these folks had to decide, was it a positive parent-child relationship that was exhibited in the story? So the data is about the mothers, and already that seems kind of weird about this study. Again, it is a controversial one. There's a lot going on with it, but we're just going to analyze the data after taking a step back from it, seeing what the data tells us so far. Any questions or comments about the data at the moment? Okay, so far, this is an interesting study. It's easy to misinterpret who even did the test. It wasn't the children. They possibly didn't even show up when the study was being done. And also, just for a little bit more background, because this was done in the 70s, the definition for schizophrenia has moved a lot since then. Back in the day, when it came to labels like ADHD, autism, and all those kinds of things, they didn't give those diagnostics very easily as a description in the 1970s. They're going by the 1968 diagnostic manual. And if a child was what we would call autistic today, in 1970, they might have been diagnosed as having childhood schizophrenia, which is really kind of crazy to think about. So it's being really old data is now part of the story here. There's a lot more going on than it seems. But nonetheless, our job is just to analyze the data as we got it. There's probably tons of biases to untangle if we had more time to think about it. And this is what happened. This is the scoring for mothers' number of stories for children deemed normal by the 1970 standard, which was pretty rough compared to today. These numbers are pretty high, some at the eights, some at the low ones, which is interesting. It's not like this parent has a difficult time with their child. It's just this parent was shown random images, had to tell a story, And someone was also subjectively saying if there's a positive parent-child relationship about it. This person scored a 1. Then on the schizophrenic end, again with schizophrenia as it was defined in the 70s for children, notice that there's a lot of lower scores. That seems to say something about the data. Lots of zeros on this. There's 1-7, but it looks like there is a difference in the data as we see it. Now our job is to analyze these data, perform a complete analysis, and we're doing this one at the 1% significance level with a hypothesis test. First thing we want to do, because it's a touchy data set, lots going on, and it's a very, very controversial one. You can Google this and learn all about it if you're curious. We want to be really careful of what we're even measuring. So that's going to be the statement phase. We want to be extremely precise when we do the planning, saying what the parameters are and what the hypothesis test even is in the first place, without putting any of our own subjective ideas or opinions into the data whatsoever. We're just going based off what they told us. And we're probably also pretending it's 1970, so we aren't giving any additional analysis based on what we know in psychology to this day. So there's no question here to say what the practical question might be, but there's an implied question. The implied question could be along these lines: is there a difference in we have to say mean or average at some point, because that's what we're measuring, not the individual observations in the population, but averages. So we'll say, is there a difference in the average? And now we have to say average of what quantity? It's a thematic apperception test. And again, I'll abbreviate that to TAT. Score. And this is, again, not for children taking the test. This is for mothers of normal children versus, and again, thinking in terms of, let's just say this is 1970, we're doing this analysis on, I'll use the same language they used, schizophrenic children. With the understanding that in 2026, probably none of those children, it's very likely to think about, there's a high chance none of them had schizophrenia whatsoever based off the new diagnostic criteria in 2026. I think they're going off 2013 if you're curious. It hasn't been updated in a little bit. So now, knowing what we're doing, we're trying to estimate a difference in the average. We know where it's about the TAT scores, and we've indicated 2 independent populations: mothers of normal children versus mothers of schizophrenic children as they defined it. That'll tell us what the parameters are, so that's our next step, and then we'll state the hypotheses. So let's get the parameters down on paper next. We'll say, let mu1 and mu2, and you can write these out differently if it makes more sense. You could say mu n for mean TAT scores of normal children, mu s for mean TAT scores of schizophrenic children if you prefer, but I'll go generically mu1 and mu2. Denote I'll say mean, but again, you could say average and that would be all right. Denote the mean. TAT score for mothers of normal children and schizophrenic children respectively. Okay, we've got our parameters down. We use the same trick that we used on the prior example. When we say respectively, we means there's a true mathematical one-to-one function where mu1 is the mean for the normal children, and mu2 is going to be the mean TAT for mothers of schizophrenic children. Now we have to do a test, so we'll say here, we will test a particular null hypothesis. The null is going to be not too bad to define. If you take a look at the notes earlier on, in the entirety of chapter 18, we're only doing one kind of null hypothesis. That is, no difference in the means. The null hypothesis is a statement of no change, no effect in the population. And this is what it would look like. We're going to say the mothers do not score differently whatsoever. The mean is 0 for that TAT test. And then we'll say against HA, we use mu1 minus mu2 again. But then we have to decide on what kind of test is this. And again, we're going based off everything they told us in the context itself. We're not allowed to look at the numbers and say the average sample average is probably higher here by a lot than the sample average on the schizophrenic group. And so we should use a greater than sign. That would be completely inappropriate. A greater than for a right tail test must be indicated in the context somewhere. So let's read through this again. Asked mothers of 20 normal, 20 schizophrenic children to compute the TAT test, score the number of stories that exhibited a positive parent-child relationship. And that's all they said. They didn't indicate a direction whatsoever. They didn't say the average score is probably higher than the normal group, and we're trying to find that, or vice versa. This one is naturally then just a two-tailed test, so we must go not equals. It'll be not equal to 0, and it'll be at the significance level stated at 1%. Alpha equals 0.01. That means there's only a 1% chance of making a type 1 error for this kind of problem. Well, that's all the preliminary analysis so far. Now we're going to start working with the data. We're going to check if the conditions are met. Then, going forward from there, we're going to run the two-sample T procedure. But again, this is a really tricky context. It's easy to get mixed up on what is being measured in the first place, what the parameters should look like in hypotheses. Any questions at all on the hard step on statistics, this preliminary analysis? Okay, now this is the fun part. Essentially, we just go back to chapter 1, chapter 2. We're going to take this raw data we see here, import it into RStudio, and see if we pass robustness. We have 20 samples in one sample, and a sample size of 20 in the other sample is a better way to say it. So we're in the large samples outcome. Doesn't mean that conditions are met by default. We also need to look at the shape of the distributions. If the shapes look like these and have outliers, a combined sample size 40 is not good enough. We need even a higher sample. And that's what this is saying right here. There are different shapes. Larger samples are needed. And what we mean by that is larger than what's being stated in any of this guidance down below. So let's go to RStudio, take that first step, import these data we see here on paper. They're also available on the Canvas webpage called example 4, I believe. So click on the import, text base. I have this on the thumb drive as usual in chapter 18. And that's what the file looks like on Canvas. So import that file. Normal schizophrenic, the quantitative variables are represented right, so you can click on import. Click away the view here. And here's our data frame. Click on play to reveal the categories. Instead of working with the entire data frame, I'm just going to extract these two quantitative variables. So I'll start by writing out norm for normal. Gets example 4. Again, go slowly, wait till it highlights because you have to type that in exactly. Then hit $sign and just click on the normal. Do it again. I'll just say skits for short. Example 4, $sign select the schizophrenic group. Then hit Control A, Control Enter just to make sure it ran. And we've got our values. So now we're going to see what are the shapes of both of these distributions right here. We're also going to check if there are outliers at the same exact time. That means Our major tools that we'd be using in chapter 2 would be histograms and box plots all at the same time. That means you might have as many 4 different displays altogether, and it gets kind of messy down here when you have 4 different pieces of graphics. So here's a really nice little piece of syntax that will give you side-by-side displays. So this is side-by-side displays in a 4x4 grid, because we'll have 4 plots, 2x2 grid. Forgot how to do the math on that. Because we'll have 4 graphics altogether. So write par, this means graphical parameters, mf row. I need to one day figure out exactly what that means. I just know it works. Then go set that equal to lowercase c 2x2. This is giving us the 2 rows, 2 columns. And then that control is done. Next, we're going to put in the histograms and the box plots. So hit write hist, normal, hist, schizophrenic. Then that's going to look into the shapes of the distributions. And at the same time, let's check for outliers using box plots. That'll involve the 1.5 IQR rule of thumb all at the same exact time. So box plot, norm, box plot, skits. We're going to have to clean up these graphics a bit. So this is just a first run to see what does it look like, to see if we're happy with our displays. Let me make that just a little bit bigger. So here's the graphs that we have so far. And notice, hey, by the box plots below, and we're going to fix up the titles of everything, but there's no apparent outliers whatsoever in our data. These are pretty far away from the main grouping, but by the 1.5 IQ rule of thumb, not bad enough to be considered bona fide outliers, again, by the rule of thumb. But even better, these are not nice distributions on their own. This is skewed to the right, and so is this one. When we think back on what robustness was saying, this is the good situation. We have more robustness when they're both have the same similar kind of shapes. So both of them being skewed to the right means our procedures are going to work well for this particular outcome. Now, we do have a requirement when we do displays like these. We should say what this is and say what the unit is. Frequency is just saying number of observations, so the Y label is just fine. So both for the normal children, let's say X label is TAT score for normal children. Again, it's about the numbers, or excuse me, the mothers, but mothers of normal children. I'll do it again for this one. X lab equals TAT score for schizophrenic children. So that takes care of the titles now. So now we have a clean axis description and unit. We now know this was just scores and what the different groups were, normal children versus schizophrenic children. Should do the same below, but below has 2 problems. We need a label for the y-axis. It's the same as this label here. And we also need to say what group this is in the very first place. So putting those 2 things together, for the normal group, we can say label, ylab equals, that entire label should be the y-axis label for the box plot. So let's just copy this in. Then do the same for the schizophrenic group. Y label equals, take that entire description, TAT score for schizophrenic children. And let's see how that looks like so far. Thinking about this a little bit further, it does indicate the group is normal children on this one. It does indicate the group is schizophrenic children on this one. So even though there's not an X label, I would say that's okay in this case. We have enough context to read what the graph is trying to say. If you put this on your report, I think that would be doing a decent job. The box plots are optional, but we absolutely need the histograms. The box plots were just for our own comfort's sake to see how severe were these observations if they qualified as outliers by the 1.5 rule of thumb. But if we want to go a little bit further, these are easy to compare when we see these different groups, because this one ranges from 1 to 7, this one ranges from 0 to 5, and same problem on these axes. So if we're trying to publish these graphics for the purpose of helping people make comparisons, the axes themselves are now misleading. So let's go the extra mile on this. Make the axes compatible on the same exact scale for both the histograms and the box plots at the same exact time. So that means we're going to control on the histogram function, xlim for the limits on the horizontal axis. Let's see, this ranges from 1 to 7, so the max is 7. This has a minimum of 0, so it should really go to 0 from 0 to 7 on both. So I'll say 0, 7 here. Do it again on this histogram. Xlim is C07. So now that we've done that, the shapes are the same, but they've moved to be a little bit more honest. And we could have arranged these differently, so it's histogram under histogram, but I decided to keep normal on one end, schizophrenic on the other end. I'm also noticing my titles, they don't look really very professional. You would have to clean that up if you want, or just delete the titles. I'm going to go that route. Delete the title here, here. Or often what I do is just take a screenshot that excludes the title, so I don't have to worry about it. If you do leave the title in, make sure it looks like something you would see in a journal. You shouldn't say norm, you should say histogram of TAT scores for normal children. Then you could probably shorten the X label title, just say TAT score instead. Okay, so with those two in, we've got the histograms cleaned up. We just want to make our scales the same on the box plots so they're better comparable at the same time as well. So for the box plots, we're going to be changing the Y limits 0 to 7 once again. So Y lim is C07. And one more run. Y lim equals C07. So lots of analysis we did on this one. Looks like a lot of code just to get some graphics out. That's only because we're being just a little bit more picky. And also, I think I broke one. Let me see what I did. Invalid Y lim value. I put 0.7, that should have been 0.7. It's the details that can make these things a little bit tedious sometimes. But now that's the condition checking side of the syntax. We take all of this, toss it back into the notes, and now we can have a complete discussion on conditions. So just a reminder, when it says check if the conditions are met, both in chapter 17 and chapter 18, if we have access to raw data, we must produce histograms, or just a histogram if it's chapter 17, then discuss robustness in terms of the shape, how it's skewed or if it's symmetric, outliers, the presence or lack of them, and the combined sample size, N1 plus N2, just the sample size N itself in chapter 17. So when we're checking if the conditions are met, this is a part right here that has to be in the notes, not just the graphics, but everything we see displayed in this text here. We have to come back to and discuss. But we got through most of the work. We produced the graphics of the data. The data don't look too bad in the context of combined sample size of 40, and the fact that the shapes are similar in the sense that they're both skewed to the right. The first thing we want to discuss was, what about the data? It didn't say anything at any point that this was a random sample, so that's one issue that we might have with these data. If you read the Journal of Abnormal Psychology way back in 1970, this exact study you might find that they have an appropriate representative sample, or maybe it was a simple random sample from a particular demographic. But all we can really say on the notes here for randomization is, this is part one of conditions. It is not known if the samples are randomly selected. So that is a big unknown in our condition checking. We should mention it as well then when we go to write this up. However, what about the actual samples themselves? We have to address if they're independent or not. And this is very plausible. One way independence could have been violated is if they took all 40 mothers and have them socialize for a while and then did the test, because then outcomes can influence each other. If people in the study had a chance to connect and to discuss things before actually doing the TAT test. But if they did this right, I would say it's very plausible. Let's say this on paper. It is plausible the samples are independent. Because the TAT score from one mother is unlikely to affect the TAT score of another mother amongst a group of normal children and schizophrenic children. But sometimes this is violated. So let me show you a context where independence is completely off the table. So let's pause on this thought. Let's go to chapter 17, but we're going into the homework assignment number 7. PDF will do just fine. And let's look into this example down at the very bottom. So this is our actual homework exercise. And notice that there is a sample for control, a sample for oligofructose, and the difference is what you would actually be analyzing in this problem. Reason you can't analyze these data whatsoever in the chapter 18 methods is the values for the control versus the oligofructose influence each other. Let's read through this context just to see how this works. Subjects took a pill for 9 days, had their calcium absorption tested on the last day. The experiment was repeated 3 weeks later. Some subjects received a oligofructose pill in the first round, and then a pill containing sucrose, that's the control, in the second round, and the order was switched for the remaining subjects. So some people, again, had the control first, others had oligofructose first. But on any single row, say row 6, the value for calcium absorption here in the control influences the value for calcium absorption here on the treatment, oligofructose, because these are data measured on the same exact patients in the first place. The values influence each other, absolutely. So this would be dependent data. But our problem is different. There is a sample of normal children, mothers giving scores that had normal children, another sample of mothers giving scores for TAT that had schizophrenic children. These are not measurements made twice on the same exact mother, and that is what gives us independence in this case. Independence could still be violated in a lot of different ways, but from what we read in the context, nothing told us that that's likely to be the case. So I just wrote, it's plausible the samples are independent. Then skipping down to condition 3, since we certainly don't know the sample means or the sample standard deviations, we'll discuss what we see in the data. Both samples are skewed to the right. So ordinarily that's problematic, but this is good for us because the shapes of the both sample data are similar. Let's say here, just to emphasize that concept, giving similar shapes. So that's one end of our analysis. This is good for us so far. Also, no apparent outliers by the rule of thumb. There are no apparent outliers by the 1.5 IQR rule of thumb. Again, if this was a problem that we're writing up for a homework, or if we were doing an analysis in an exam 3 situation, we'll do these kinds of things in an exam 3 problems. It still doesn't end at this step because we have to also discuss at the same time, how did the sample size influence all of this? If these were our data and the sample sizes were, say, 5 in both groups, this is a big problem for us. Or if one sample had 5 and the other one had 12, very unbalanced and unequal and low at the same time, we're still in trouble. So we look into the sample sizes, we go through our guidance from our author, which is very generic and conservative at the same time. We're in this situation. The combined samples for our study is 40, and so we're in the large sample end. Even though there was a good amount of skew, we can absolutely overcome that. The two sample T procedures are actually highly accurate in this context, even with data that looks as bad as that. It's kind of surprising. So here's what we'll say all together. Since the sample sizes, let's say this differently, the combined sample size is sample size 1 plus sample size 2 equals 40 is large. The robustness conditions are met. So that was all of the heavy lifting in the entire problem, doing the analysis of what the parameters are, then checking the conditions after saying that, writing down the hypothesis test. We're about out of time, but just because we're almost there, I want to show you what the syntax is going to look like when we come back on Wednesday to finish off this problem. The actual test itself is really, really fast. It goes like this. We go t.test. Again, for doing this by scratch, pen or pencil and a calculator, it's much like what we did in the prior problem. But if you have the raw data like we do, this is all you have to put in. Put in one group, the normal children, put in the next group, schizophrenic. Then we have to be mindful that it's a two-tailed test. So let's make sure that we have alternative, type it slowly, alternative equals. It tells you that there's greater than, less. That's the right-tailed, left-tailed test. But ours is two dot-sided with quotes. So alternative equals 2 dot-sided. So run that. And this is the entire test altogether. Welch two-sample test tells us we never assumed equal variances. It gives you the test statistic, runs through the tricky formula for degrees of freedom, and we have a very, very small p-value. So it looks like there is statistical significance that we're going to write up when we conclude on this problem on Wednesday. But I just want to show that last step just because we got so close. And we did all the hard stuff getting up to this point. Well, any last questions at all, folks, analyzing these data? Okay, I'll post the syntax we use to do all this analysis here as well at the end of the notes. And again, we'll finish this problem out later when we come back on Wednesday. But if you're curious about this problem, again, there's a lot to say about it. It goes way beyond this class, but this is probably the most controversial data set we'll see in the entire semester. Lots of things you could talk about with it. All we're doing is giving an honest analysis based on the data we saw. But have a great afternoon, folks. We'll be back to this on Wednesday's class.